Now, today we are going to start a new theory, that is, it is also known as Paulson-Moffat's model, or it is also known as concept of maximum overlap of carbon orbitals. It is also known as bend bond theory, and it is also known as banana bond theory. Now, this is a laughing concept, that is why it is called as banana bond theory. So what will be the today's point? We are going to cover with respect to the cycloalkanes, Coulson-Moffat's model, concept of maximum overlap of carbon orbitals, also called as bent bond theory, or it is also known as banana bond theory. Now, what is the reason behind why it is known as bent bond theory, or it is also known as banana bond? It is a type of covalent chemical bond with a geometry, somewhat indicative, somewhat resembling, somewhat looking similar to that of banana. Now, the term itself is general representation of electron density. What type of term? That is, in this case of this model, there is a maximum overlap of carbon orbitals occur. We know the orbitals of the carbon, how they are going to overlap with sigma bond, how they are going to overlap with the pi bond, which type of orbitals are involved in the overlapping when they are going to form the bonds, either sigma bond or the pi bonds. So we know these points, that is the term itself. Which term? That is concept of maximum overlap of carbon orbitals is then representation of electron density or configuration resembling a bent structure with a small ring molecule such as cyclopropane. So in case of Bayer strain theory, we have discussed that the tetrahedral bond angle is 109 degrees and 28 minutes. But when they are going to achieve the structure of cyclopropane, they are deviating from the normal bond angle and they are going to achieve the structure that is triangle. In this case also, with respect to the cyclopropane, they are bending from the normal structure, or it is a representation of double or triple bond, which is looking when the carbon atoms are hybridized with sp2 and sp. This is an alternative to the sigma and pi bond. We will discuss the diagram so you come to know about this in detail. Now, this is an overlap of Coulson-Moffat model. See, we have discussed with respect to the cycloalkane that according to Bayer's string theory, in this structure they are deviating from the normal bond angle. This is proposed by the Bayer. But Coulson-Moffat model or the maximum overlap or bent bond or the banana model, what they are going to suggest us that when they are overlapping, see, these are the pi orbitals of the two carbon atom. This carbon atom along with this carbon atom and this carbon atom with this carbon atom. So all the carbon atoms of the cyclopropane molecules, they are overlapping with their pi orbitals. So they will bend their structure in this manner and they are going to form the resemblance bond as like that of banana. That's why these bonds are known as banana bonds. Now, when they are overlapping, see, the normal overlap with the sigma bond is in this manner, 360 degrees centigrade. Oh, sorry, 180 degrees centigrade. But when they are going to bond with respect to the cyclopropane, they will bend their bonds. And these bend bonds, after the completion of structure of cyclopropane, they will achieve a structure of banana. That's why this theory is known as banana bond theory. See here, atomic orbital overlap with respect to the cyclopropane. So in this manner, they are going to do their overlapping of p orbitals. This is an bonds which we have drawn. But theoretically, but the actual bond conformation, but the actual bond conformation is in this manner. That's why this theory is known as banana bond theory. So when we are going to draw the plane structure, normal plane structure, this is in this manner. But when they are in space, actually overlapping with each other, they are going to achieve the structure like banana. That's why this theory is known as banana bond theory. Now note that sigma bond, which is strong bond, which is formed between the two carbon atoms, involves end-on overlap with the pi bonds. This is an p orbital of this carbon atom and this is an p orbital of this carbon atom. So they are going to overlap with the end bond overlap, involves side long overlap. When bond is intermediate between, so this whatever this bond is formed, which is an intermediate of sigma and pi bond. So the overlap being neither end on or neither side long. This is not the normal bond which is formed, stretchable bond. So they are going to bend their structure as it is an intermediate between the sigma bond and pi bond. So this makes the overlap less efficient than the sigma overlap with respect to the cyclopropane, and the carbon-carbon bonds weaker than the normal carbon-carbon sigma bond. As there is bending between the carbon bonds, due to this bend, these bonds are weaker than the normal sigma bond. See, in this manner there is formation of normal sigma bond, but due to this bending overlap with respect to the cyclopropane molecule, this bond is weaker than the normal sigma bond. And this all will be proposed by the Coulson-Moffett. That's why this theory is known as Coulson-Moffett model of cycloalkanes. I hope it is understood to everybody, this model. Now, we have discussed Bayer-Strain theory. We have discussed Coulson-Moffat's model. Now, we will correlating these two models. Which models? Bayer-Strain model and Coulson-Moffett model. Now, in depth, we have discussed with respect to the Bayer-Strain theory. What is Bayer-Strain theory? According to Bayer-Strain theory, the configuration of cyclopropane is in which manner? Triangle manner. With a carbon valency angle 60 degree. We have discussed the structure. They are going to form the bonds at an angle of 60 degree centigrade. All the carbon atoms. This value is impossible as the carbon valence angle can never be less than 90 degree centigrade. According to Bayer, what he has proposed, when cyclopropane is going to achieve the cyclic structure, he is going to form the bond angles at 60 degree centigrade. But this is not possible. That's why cyclopropanes are less stable. What is the possibility? Whenever cycloalkanes are forming a ring structure, they are not going to form a bond angle less than 90 degree centigrade. When the p orbitals are overlapping with the carbon atoms. त्यांचा normal bond angle 90 degrees असला पाहिजे. That's why this theory has their own limitation. म्हणूनच Bayer-Strain theory ला तिचे limitations आहेत. Now, the angles are more than 90 degrees centigrade when they are going to which state? Hybridization state. So, according to Coulson-Moffett proposed that the smallest carbon valency angle which one can reasonably expect is 104 degrees centigrade. When the carbon atom is in tetrahedral angle, sp3 hybridized, that time the bond angle is 109 degree and 20 minutes. But according to Coulson and Moffett, whenever any carbon atom is undergo hybridization, it should achieve the bond angle above 90 degrees centigrade. Above 90 degree means at least 104 degrees centigrade. Therefore, he suggested that in cyclopropane, only a partial overlap of sp3 hybrid orbital occurs. So he has proposed that whenever carbon atom is undergo sp3 hybridization, there is a deviation from the bond angle, that is normal bond angle 109 degree and 20 minutes. Now, how much deviation will be allowed? This much, that is 104. So therefore, he suggested that cyclopropane only a partial overlap of sp3 hybrid orbital occurs. So the carbon-carbon bond angle is decreased slightly from 104 to 109 to 104, and the hydrogen carbon and hydrogen angle increased to 120 degree compared to the normal tetrahedral angle. That means carbon-carbon bond angle is decreased from 109 to 104, and hydrogen-carbon hydrogen bond angle is increased to 120 degree centigrade. 120 degree compared to the normal tetrahedral. This decreasing in the overlap results in weakening of the bond. As they are decreasing their deviation, the decreasing bond angle from 109 to 104 will weakening of the bond, and therefore explains the instability of the cyclopropane. That's why, as they are not going to achieve the normal bond angle, they are unstable than the normal cycloalkane. In the case of cyclobutane, also has a pain bond, but the decreasing overlap is less than the cyclopropane. cyclobutanच्या बाबतीत पण सेम फिनॉमिनन होतीये, पण त्यांचं जे काही डेव्हिएशन आहे इट इज लेस as compared to the cyclopropane. So cyclobutane therefore more stable than the cyclopropane and less reactive than the cyclopropane. Stability and reactivity inversely proportional. More will be the stability, less will be the reactivity. That's why cyclopropanes are more reactive than the cyclobutane. According to which theory? Kurzil-Moffat's model, banana bond theory. Increased stability decreases reactivity. Increased reactivity decreases stability. So this is about second model with respect to the cycloalkanes, that is banana bond model, Kurzil-Moffat's model, maximum overlap model, and bent bond model. These are all same with respect to the carbon-carbon sigma bonds. When they are in cyclopropane and cyclobutane, there is slight bending of the bond. When they are going to form a sigma and pi bond, they are going to have the properties in between the sigma and pi bonds. These are all with respect to the Kurzil-Moffat's model. Now our next theory is Sashe-Mohr theory. This is also known as theory of stainless steel. Now this is our last theory with respect to the cycloalkanes, that is Sashe-Mohr theory. Now, according to Bayer, we have discussed they are deviating their angle from the normal tetrahedral bond angle. The carbon atoms of the ring are all in the same plane. We have discussed the features of Bayer's string theory. So in that, the first feature is all the carbon atoms in the ring are in the same plane. So we have discussed this is the first feature of Bayer's string theory. The strain was calculated. Strain means pressure which is calculated on the assumption that cyclic rings are planar. Whatever angle strain we have calculated in the case of Bayer's strain theory, the strain is that the rings are planar in nature. The strain is minimum for the cyclopentane. We have discussed. Strain means deviation, which is minimum in the case of cyclopentane. When we are comparing with the cyclopropane and cyclobutane. Cyclopropane आणि cyclobutanशी जेव्हा आपण angle deviation compare करतो त्यावेळी cyclopentanचा angle deviation हाच कमी आहे. The strain is minimum for the cyclopentane and goes on increasing as the size of the ring will increase. Hence, members higher than the cyclopentane should be increasingly unstable. According to which theory? Bayer's strain theory. सायक्लोपेंटेनच्या वरती जर आपण नंबर ऑफ कार्बन ॲटम्स इन्क्रीज केले किंवा रिंग वाढवली तर अकॉर्डिंग टू बेअर त्यांची स्टॅबिलिटी वाढत जाते. बट पॉसिबिलिटी काय आहे? मेन पॉसिबिलिटी इज or the reason is they are unstable. But Hermann Sashe soon pointed out that the scientist, that is Sashe, pointed out that large rings need not be strained. There is no any deviation of the angle. There is no any strain in the larger rings because what is the reason behind that? Because the carbons need not be coplanar. What Bayer has proposed? Bayer has proposed that when they are in the cyclic structure, they must be planar. But according to sashe theory, when there is increasing in the ring size, ring carbon atoms, there is no limitation, there is no any restriction for those carbon atoms, they should be planar. Now, Sashe-Mohr theory proposed that higher member ring can become free from strain. According to Bayer, they are going to have the strain, angle strain, as they are deviating from the normal bond angle. But according to Sashe-Mohr theory, they need not be planar, they need not be achieving the strain. If all the ring carbons are not forced into one plane, if we are not going to attain the one plane structure with a larger ring, they exhibit in two non-planar cumma folded or puckered conformation. They need not be planar, they need not be straight, they need not be planar, and they are going to achieve what type of structure? Folded structure or puckered conformation, both of which are completely free from the strain. They may achieve any structure, any conformation which is free from the strain. There will not be any limitation for those carbon atoms. They are going to form the bond in this manner or given manner only. These are strainless. There is no any strain as the carbon atoms lie in different plane and the normal valency angle is 109.5 is retained. They may achieve any conformation. They may change their structure. How? By retaining the bond angle 109, that is tetrahedral bond angle. These type of conformations are called as chair form or the Z form, and the second conformation which is achieved by the higher rings is boat form or the C form because of their shapes. So we will discuss these shapes and the structures. So this is an boat conformation of cyclohexane. See, here we can compare the Bayer strain theory and Colson-Moffett model. Majority of the case we will compare this model with the Bayer strain theory. According to Bayer strain theory, there is deviation from the bond angle. They may give the strain to the carbon atom. But in the case of this conformation, there is retention of the bond angle, that is 109. They may change their structure in any conformation. There is no any strain is involved in the ring, and the structure may not be planar. So these two type of structures will be achieved by the higher rings. What are those two types? Boat conformation and chair conformation. As it is looking like boat, that's why this conformation is known as boat conformation of which compound? Cyclohexane. Higher rings above the cyclopentane molecule. And chair conformation of the cyclohexane as he is going to achieve 6 axial and 6 equatorial hydrogens. What is the meaning of the word axial? When they are perpendicular to the plane, that type of hydrogens are known as axial hydrogens. And when the hydrogens are parallel to the plane, these type of hydrogens are known as equatorial hydrogens. In this case, each carbon atom look like tetrahedral. See here, if we are considering this carbon atom will looking as a tetrahedral geometry. Every carbon atom in this conformation is looking like the tetrahedral geometry. Now, the chair conformation is the most stable conformation of the cyclohexane. Why? What is the reason behind that? Why this conformation is most stable conformation of the cyclohexane? Because bond angle is achieved 109. All the carbon atoms of this conformation is going to achieve what type of geometry? Tetrahedral geometry. Hydrogen atoms of this conformation are equally divided into axial hydrogens and equatorial hydrogen. They will not interfere each other's conformation. That's why this conformation is more stable with respect to the cyclohexane. In chair cyclohexane, there are two types of positions: axial position and equatorial position. Axial means perpendicular to the plane of the structure, axial position. Parallel to the plane of the structure, equatorial position. The axial position point perpendicular to the plane, whereas equatorial positions are around the plane of the ring. So, Mohr further elaborated this theory and applied it to the compounds higher than that of the cyclohexane, that means cycloheptane, octane, cyclonone, and cyclodecane. So this theory we can apply it for higher than the cyclohexanes. So